SwayamPrabha. Digital India. Educated India.
I welcome you all to the session of Thermal Engineering Basic and Applied. Today we shall discuss about the engine operating characteristics, and in this context we shall introduce a term which is MEP. The full form is mean effective pressure. What is mean effective pressure, and if we discuss the engine operation, the role of mean effective pressure is very important, and also we shall discuss about the indicator diagram. You know, we were discussing about the carburetor in the last a few classes, and we have seen that internal combustion engine or any heat engine, when we design, the sole purpose is to get work output, and to get that work output, particularly for the spark ignition engine, carburetor is an important element. For the compression ignition engines, carburetor is not an essential part, but the combustion is initiated by utilizing the the high temperature, rather the thermodynamic state of the fuel that is there in the combustion chamber at the end of the compression stroke. So, now to analyze the engine operating characteristics, particularly focusing on the mean effective pressure, what we need to do? We need to draw the schematic of a 4-stroke engine. Maybe we shall discuss everything in the context of 4-stroke engine, but eventually the relation, several expression that we shall try to drive in today's class also can be written for the 2-stroke engines. So, if we draw the schematic, this is the top dead center and this is the bottom dead center, and piston is having reciprocating motion between these two centers, TDC and BDC. Now, we have seen that air will be, so we can see that the piston is having reciprocating movement between these two centers, and we need to induct air if it is a CI engine or air fuel mixture through this intake manifold to the engine cylinder, and piston is having movement between these two stops, and we have identified several strokes. So, today we shall discuss about the work output. This is very important, because you know that no matter whether you are supplying only air or air fuel mixture for the CI and SI engines respectively, our sole purpose is to get work output at the cost of some energy, that is the energy which is remaining stored within the fuels being supplied. So, the work output, you know that that is the work generated inside the combustion chamber of the cylinder. So, the air fuel mixture or air which would be eventually mixed with fuel for the CI engine during the end of the compression stroke, the sole purpose is to have perfect or efficient combustion, and it is because of the combustion, due to the gas pressure, a force will be acting on the piston face, and it is because of that force piston will have movement, or piston will travel from TDC to BDC. So, we will be getting work output. Now, so this is the work which is generated by the gas inside the combustion chamber of the cylinder. So, this is the work output. Now, what we know, because we know the work is basically the force which is acting through a certain distance. If we can calculate, then we can get the expression of the work output. So, say that piston has displaced this small distance dx because of the gas pressure which is there inside the combustion chamber, and then what would be the expression of work done? So, you know that the force due to the gas pressure which will be acting on the piston face, if we draw the 3-dimensional view of the piston, then piston face to be precise. So, this is the piston face on which force due to gas pressure will be acting. Now, if we assume that the pressure is P inside the engine cylinder, so the force, we can calculate. So, work done would be integral P into A. We are assuming that the area of this piston face is A, and it is because of this force the piston has traversed a distance dx, right. So, this is the expression of the work done. Now, we need to know this particular quantity to estimate the efficiency of the engine, because what we are doing, whether we are going to have a carburetor or we are going to have different other arrangements for its operation, the sole purpose is to get this amount of work done. So, this we can write it P into dV, because this A into dx, this quantity is dV. So, this is the differential volume displaced by this gas. So, so this is the differential volume. So, this is the differential volume displaced. So, piston has displaced by an amount dx. So, this is the differential volume. Now, question is, see, this is basically the pressure which is very important to predict the amount of work we will be getting inside the engine cylinder. We shall discuss about several terms of the works that we need in the context of this engine operation, but the pressure P, it is very unlikely that the pressure will remain constant throughout the process. Rather, as the piston is travelling from TDC to BDC, pressure will keep on changing, and if the pressure changes, we cannot analytically calculate what would be the work done. So, we need to go for some computational analysis to calculate what would be the work done, because you know that this is the elemental volume which is displaced. Now, if that pressure is P, then we can get this expression. For another elemental volume, pressure P may change from P1 to P2, let us say. Not only that, inside the engine cylinder, if we traverse spatially, rather there would be a spatial variation of the pressure. So, it is not so easy to calculate the work done, provided if we introduce another term. So, what we have understood is that we can calculate the work done, rather work output from this expression, but it is not so easy to calculate integral PdV, that is that is basically summation. So, basically if we can calculate what is the pressure at each and every point inside the combustion chamber, and because essentially piston will have the change in volume from VTDC to VBDC. So, this dV is VTDC minus VBDC, right. So, this is let us say delta V. So, volume will be changing like this, but it is very unlikely that for a change in volume from TDC to BDC, pressure will remain same throughout the process. So, it is a continuously, it is changing continuously as the piston moves from TDC to BDC. So, to get the expression of the work done without going into much complex computational analysis, we can introduce the concept of mean effective pressure or average pressure. So, now let us see why that mean effective pressure or average pressure is very important, because this pressure will keep on changing as the piston traverses from TDC to BDC, but if that is the case, it is very difficult to get the expression of work done without involving the computational analysis. Instead, what we can do, we can qualitatively, I can't say not qualitatively, we can estimate the work done by considering or by invoking the concept of mean effective pressure, and that is what is very important in the context of engine operation. Now, you know that engines are multi-cylinder very often, and if engines are multi-cylinder, then it is convenient to analyze the engine cycles per unit mass of the gas in the combustion chamber, because multi-cylinder engines will be there. It is quite often that engines are multi-cylinder. So, for multi-cylinder engines, instead of writing the expression of work done in this form, it is better to write in the specific form, that is to express or to analyze the engine cycles per unit mass of the gas in the combustion chamber. So, what we can do, we can write this small w, that is W by M, equal to P small dV. So, basically what we can write the expression of work done, W is equal to minus P dV. As we have discussed about the need of mean effective pressure, rather need of the concept of the mean effective pressure. So, instead of writing this, because you know that what we can do, we can calculate pressure at each and every location inside the cylinder, and if we know the change in volume, then we can sum up. So, multiply that pressure with the change in volume and we can sum up, that is the integration. So, what we can write? We can write it, this is mean effective pressure into delta V. So, this is the work done. So, from this expression, so instead it is not so easy to calculate this integration, provided we know the pressure at each and every point, and that is very difficult to solve without the help of much complex computational analysis. Instead we can write this, and from there we can write the mean effective pressure equal to W by delta V. So, this is basically you can see that we have written both the quantities both in numerator and in denominator in their specific form. We also can write like this, W by V d. So, this is basically displacement volume. Okay. So, this is the displacement volume. So, you can see that mean effective pressure is very important to quantify the work output from the engine, provided we know the displacement volume, but this quantity is always known, because the engine designer designed the engine for a certain stroke length. So, that is the we very often we discuss about XCC engine, YCC engine, ZCC engine. So, what is the meaning of that CC? So, basically the that the stroke volume, that is the total displacement volume of the engine cylinder. So, you can understand that the work output will depend on this displacement volume. So, higher is this volume cubic centimeter, CC is cubic centimeter, that is the stroke volume or displacement volume. Higher is the displacement volume, higher will be work output. So, the engine will be much more powerful. So, that is the objective. Now, this mean effective pressure, if we just look at the expression which is written in terms of the specific quantities both in numerator and denominator, W by delta V, and this delta V is basically V TDC minus V BDC. Okay. So, this is the change in volume. This work, as I was just discussing, let us discuss this particular point. Think that the work which is produced inside the cylinder, that work may not be available at the crankshaft because of the mechanical friction. That is what we have studied. So, basically the work mechanical friction that would be there, that we have studied, because these are the mating parts. So, the piston will be having to and fro movement, and frictional loss between these two mating parts will consume certain amount of work that is being produced. So, the work which is available on the piston face inside the engine cylinder is not available at the crankshaft, because the frictional losses are there or frictional loss is there. Over and above that frictional loss, that some parasitic loads are there. What are those parasitic loads? Because that we need to run a pump which will sprinkle the lubricants. So, to run that lubricants pump, to run the compressor, because sometimes we need to have compressed air, also air conditioner, because in most of the cases we will be having air conditioning unit also. So, to run all those units, some energy is needed. So, the parasitic loads include the amount of work which would be required to run all those devices. So, the frictional loss between the mating components alongside the parasitic loads, these two effects reduce the work which is available at the crankshaft. So, you can understand this mean effective pressure, we can have several mean effective pressures depending on the work or different work. If this W is the work which is available, which is available at on the piston face inside the cylinder, then mean effective pressure will be something. If we consider the work which is available at the crankshaft, then mean effective pressure will be have different name. So, if we now go to discuss about the mean effective pressure, several mean effective pressures. So, basically we have first IMEP. So, this stands for indicated mean effective pressure. Similarly, we will be having BMEP. So, this is brake mean effective pressure. We may have FMEP. So, this is frictional mean effective pressure. Okay. Why all these terms? So, see, just we have added one prefix I for indicated, B for brake, F for frictional. So, we are trying to introduce different works, that is indicated work which will corresponds to indicated mean effective pressure. If it is brake work, that work will correspond to brake mean effective pressure. If it is frictional work, that work will correspond to frictional mean effective pressure. So, basically at least from several mean effective pressure that we have written over here, we can see that different works are available in the context of internal combustion engine operation. So, if we go, the work which is available on the piston face or available inside the combustion chamber is the indicated one. So, that means this is the indicated work. So, if we write here, if we write work available inside the combustion chamber. So, that is Wi or Wi and IMEP will be equal to Wi by delta V. For the same engine, delta V is fixed, only the work which is available inside the combustion chamber is the indicated work, and if we define the mean effective pressure considering indicated work, it would be indicated mean effective pressure. Similarly, work available at the crankshaft, and this is the WB or brake work. So, this is the brake work and if we define the mean effective pressure based on the brake work, that would be WB by delta V. So, the work which is available at the crankshaft, that is the brake work, but the work which is available at the inside the combustion chamber is the indicated work. You can understand, that means these two works are not same. So, if they are not same, some amount of work is needed to overcome the friction and other parasitic loads that I have already discussed. So, that work is known as WF or WF, and if we define frictional mean effective pressure, that equal to WF by delta V. Try to understand, this work is not obtainable from the engine, because this is the amount of work which is lost to overcome the frictional loss, alongside to run several devices to get the auxiliary facilities in the internal combustion engine. So, this is all about I mean effective pressure, brake mean effective pressure, indicator mean effective pressure or IMEP, brake mean effective pressure or BMEP, and frictional mean effective pressure or FMEP. So, try to understand, from here at least we can write that this W indicated is equal to W brake plus W friction. So, what we can write is brake work is W indicated minus W friction. Whether I am writing in their specific form or the actual form, that is irrelevant here. So, I could have written these quantities in their specific form as well. So, what we can see from this particular expression, that this is the work which is not realized in practice, this is the work which is available inside the chamber, while this is the work which we get at the crankshaft. So, basically at the cost of some energy, eventually you are getting this amount of work, though the work which is produced inside the combustion chamber is even higher. So, certain amount of work is not available at the crankshaft. In other words, that amount of work is getting lost for some parasitic loads as well as to overcome the friction. So, from there we can define one efficiency, because you can understand. So, WB is not equal to WI minus, not equal to WI, rather it is slightly less than WI. So, can't we write it that, if we write it that WI WB equal to WI minus WF. So, this is WB is less than WI. We really do not know. So, that means WB is not equal to WI. So, we can write it is equal to WI multiplied with certain factor, and that factor is eta m. Certainly, the factor eta m should be always less than 1, and this quantity is known as mechanical efficiency of the engine. Okay. So, basically we can define eta mechanical equal to WB by Wi. So, the fraction of work which is available at the crank shaft of the indicated work is the eta m. So, this quantity is always less than 1, and our objective should be to get more brake work, so that the mechanical efficiency of the engine would be higher. Okay. So, that we have talked about all these things. Now, we have discussed about the need of mean effective pressure in the context of engine operation. From there, we have defined several mean effective pressures using different forms of work. Now, we have talked about indicated work, we have talked about brake work, we have also talked about the frictional work. Now, that if we try to recall the basic cycle which we have probably discussed in the beginning of this course in this particular module. See, as we have discussed that parasitic loads. So, we need to run compressor, we need to run air conditioning unit, we also need to run some pumps if needed, because as I told you that we need to supply continuous coolant to reduce the temperature of the engine cylinder. So, if the coolant should be circulated continuously, so that circulation pump should be there. To run all these mechanical devices, certain amount of power is needed, and that power will come from the power that is getting produced. So, if we try to look at all these devices consume power, and those are known as negative power. So, basically positive power is the indicated power or indicated work that is available inside the combustion chamber, while the negative works, that is frictional work and other works to overcome the to run for the parasitic loads, we need some negative work, and that some work, and that work can be viewed as the negative work in the from the perspective of this engine operation. So, let me talk again. Indicated work is the positive work or brake work is the positive work. Now, brake work is directly measured at the crankshaft, while indicated work is not measured. However, now the work, a part of the work that is needed to overcome the frictional loss, also to run several devices for the parasitic loads, the work needed can be viewed as the negative work. So, positive work is the brake work, while negative work is the frictional work and associated works which are needed to run for several devices. So, with this now we have seen that it is convenient to define mean effective pressure. Now, let us briefly discuss about the indicator diagram. What is indicator diagram? Why it is so important, and should we get anything from this indicator diagram? Now, you see that we have discussed that W is equal to integral P dV, and that P is the pressure at any point inside the cylinder at any moment. So, that pressure is continuously changing, volume is also changing, but eventually if we know the total volume integral dV from 1 to 2, because eventually we need to integrate from VTDC to VVDC. So, we know the total change in volume would be VTDC minus VDC, but while changing the volume from VTDC to VVDC, pressure is continuously changing. So, let us now look into the change in pressure along with volume, or change in pressure with the change in volume as the piston is travelling from VTDC to VVDC. Now, the diagram which is used to represent the change in pressure with the change in volume as the piston is travelling from TDC to VDC and again going back to complete one cycle, that diagram is known as indicator diagram. So, let us draw this diagram. So, if we draw, this is indicator diagram. So, we can draw as we have mentioned that we need to see the change in pressure in with a change in volume, definitely we need to map the processes in PV plane. What are the processes? Basically you know that compression, expansion, power and exhaust. All these 4 processes to complete one cycle of a 4 stroke engine, be it a SI engine or be it a CI engine. So, let us quickly identify so this is VTDC and so this is VBDC. Definitely you know VTDC is less than VBDC because this is the clearance volume, right. Volume is not, so still we need to provide some volume and that is the clearance volume. Okay. And you know that if we draw, rather if we try to map several processes. So, this is PATM, atmospheric pressure. So, all valves are now closed. This is the atmospheric pressure outside the engine cylinder. What we do? We say we are trying to take the we are bringing the piston from TDC to BDC. So, if we go back to this diagram, so we will be bringing piston from TDC to BDC. Okay. So, if we do this, then pressure inside the cylinder will be less than atmospheric pressure. So, we can represent, so piston is coming from this point and it will be like this. Piston is coming from TDC to BDC, pressure inside this engine cylinder should be less than the atmospheric pressure and it is because of this pressure difference either air fuel mixture or pure air will rush into the engine cylinder, and that is what we have seen using from the basic discussion as well as the carburation. Now, when the piston is at BDC, then next stroke is the compression stroke. So, intake valve will be closed, but in real practice intake valve will not be closed immediately when piston start travelling from BDC instead. So, if we draw it, so if the piston start travelling from BDC, it will again come to TDC and the process is like this. So, our entire objective is to reduce volume to increase pressure, right. So, the curve will be like this. Okay. So, volume is getting reduced, pressure is increasing, and that is the object. Now, ideally we should close the intake valve when piston is at BDC, but it is not the case. We shall discuss all these things later. So, what is done? You know, if I mark here, then this is, it is not exactly at BDC, but slightly when the piston is slightly away from BDC during the compression stroke, here this is the point. So, intake closes, intake valve closes, okay. And then exhaust is remaining closed and you can see the exhaust is remaining closed, but now intake closes. So, we can see the pressure rise. If we talk about the spark ignition engine, or if it is not the spark ignition engine, compression ignition engine, at the end of the compression stroke combustion will be there, and it is because of this combustion there will be a rise in pressure and temperature inside the cylinder. So, pressure will rise abruptly, but if it is a spark ignition engine, we need to switch on the spark plug. When we need to switch on the spark plug? So, it is automatically, it is nowadays it is electronically controlled unit. So, spark plug switch will be on when piston is slightly away from TDC during the compression stroke. So, here this is the spark. So, this is point 1, this is point 2. So, 2 is spark plug switch on. Okay. So, this is spark plug switch on, and 1 is intake valve closes. And then, so if it is spark plug will be needed to initiate combustion, or if it is CI engine there is no requirement of spark plug, and combustion will be fuel will self ignite, and what will be there? There will be huge rise in pressure. So, pressure will rise like this, and then at the end of the compression stroke when piston is at TDC, pressure will be like this, and then again piston will come back from TDC to BDC, pressure will fall, that is the power stroke, and it will be like this. Okay. And you know that piston has it is so okay. So, piston has arrived at VDC, still some amount of pressure is there. Should we now piston is at BDC, next stroke is exhaust. So, we need to open the exhaust valve. So, you know that this is again piston will travel from BDC to TDC. When piston is travelling towards TDC, we need to open the exhaust valve. So, this is 3. Before reaching piston at BDC, exhaust valve is allowed to open, so that the pressure inside the cylinder will reduce, and when piston is coming back from BDC to TDC again during exhaust stroke, we will face relatively lesser resistance. That is the objective. So, that is why this valve, exhaust valve, is allowed to open when piston is about or is yet to reach at BDC, little away from BDC. So, 3 is exhaust valve opens, and then piston is coming from BDC to TDC, the combustion gases inside the cylinder will go out from the chamber, and then when piston is coming to TDC, ideally we should open the intake valve, but what is done in reality, you know that so exhaust valve is remaining open, but intake valve should, I mean ideally intake valve will again open when piston is at TDC, but in reality what is done, intake valve is allowed to open when piston is yet to reach at TDC. So, this is 4. So, not exactly when piston is reaching at TDC, but when piston is yet to reach at TDC, slightly away from TDC, the intake valve is allowed to open. Again there is a logic behind it, because if we open the intake valve, exhaust valve is remaining open, the opening intake valve will allow fresh charge to come in, and that fresh charge will allow the exhaust valve, the exhaust gases to completely remove from the engine cylinder, but it is not even possible to complete removal of the exhaust gases. So, you know that ideally at TDC intake will open and exhaust will closed, but we are allowing intake valve to open when piston is little away from TDC during exhaust stroke. So, that fresh charge will come and that fresh charge will allow exhaust gases that would be there in the clearance volume to remove from the engine cylinder. That is why exhaust valve is remaining open until piston is again travelling back from TDC to BDC during next cycle intake stroke. So, this is exhaust valve is allowed to close when piston is little away from TDC during next cycle intake stroke. So, try to understand, which is really interesting, that this is say 5. So, 5 is, so I can write 4 is intake valve opens, 5 is exhaust valve closes. So, what is interesting, this is the part of the total process wherein both the valves are open, are remaining open. So, both valves are remaining open in this part of this total process. So, 4 intake is allowed to open, exhaust is remaining open until 0.5. So, this is known as valve overlapping in this indicated diagram. So, we have tried to map all the processes for 4 stroke cycle engine. If it is, so this is sparking. Now, if it is not the SI engine, then 0.2 will not be there, because we will be utilizing the self ignition properties of the fuel. But the diagram that we have drawn today is for the 4 stroke cycle engines, and what we can see that we have mapped several processes to complete a cycle of a 4 stroke cycle engine, and from there we have understood several timings of valve opening, both valve, I mean both intake and exhaust valves, and we have also identified an interesting point that there is a regime in which both valves are remaining open, and this particular zone is known as valve opening. So, this is known as valve overlapping, sorry, this is valve overlapping. So, as if this is valve overlapping. So, basically both valves are open. So, need of allowing both valves will remain open, we have discussed, because we are allowing intake valve to open when piston is little away from TDC during the end of exhaust stroke, because if we do so, then fresh charge will come or fresh air will come, and that fresh charge or fresh air will allow the combustion gases which will otherwise remain there in the clearance volume to go out from the engine cylinder, because the exhaust valve is already open, and that is why we are not closing the intake valve again exactly at TDC. Instead, we are allowing exhaust valve to close at 0.5, that is little away from TDC during the intake stroke of the next cycle, and in this particular regime or in this particular zone, the both valves are remaining open and it is known as if two valves are overlapping each other. So, that is called valve overlapping. So, if we summarize, today we have tried to discuss about the concept of mean effective pressure relating with the engine operation of both SI and CI engines. From there, we have introduced several mean effective pressure by using different works, and finally, we have talked about the indicated diagram, which is very important. And if we look at the positive work, that is the brake work that we are getting, that is the, if we try to hatch the portion. So, this is the PV diagram. So, integral PdV. Now, this is basically, if we try to hatch, so basically this is the positive work, right, while the work that is below PATM, that is the negative work. So, you know, we have talked about both positive and negative work, because brake work is the positive work, while negative works are the work, a part of the indicated work which is needed to overcome the frictional loss and to run several devices for the parasitic as a parasitic loads. So, we have discussed this indicated diagram, and quite interesting to see that there is a zone in which both valves are remaining open, and we have discussed about the need of allowing both these valves to be opened in this particular zone, and this is known as valve overlapping zone. So, with this I stop here today, and we shall continue our discussion in the next class. Thank you.